Doors are closing, so I guess it's go time. You're all stuck in here with me now for the rest of the hour. Hello. All right, good afternoon, NDC. How are you all doing? Having a good conference? Yes. Yeah? Had some good food? Had way too much food and now ready for an hour of deep dive into some code and not fall asleep?
We will see.
First one who snores loses. All right. Today, the next hour, we'll be talking about HTTP client. And the main reason I decided to do this talk is because, well, we all use HTTP client, right? Well, obviously, otherwise you wouldn't be here. Is anyone here not a .NET developer, by the way? Okay. I hope you learned something of .NET. This is very, well, partially it's very specific .NET implementation, like how does .NET do these things? But the main things that I'm showing here, that I'm trying to prove, also work in other languages. The very first time I delivered this talk was for a group of students who I was not informed up front were all Java students. So that was a very interesting version of this talk, but I guess they learned something. It's very nice to meet you all. My name is Nico. I'm a cloud solution architect at Microsoft in Belgium. I used to be an MVP for 12 years, I believe. And then in Belgium, I do some community stuff. I run some user groups. I run some conferences. That's about it. If you want to follow me online, I'm mostly active on Blue Sky and LinkedIn. So those are the two platforms that you can find me. If you have any follow-up questions after this talk, reach out, talk to me in the hallway, come up here while I'm packing my stuff up. That's all good. OK. So why should you care about HTTP client? Why should you be here in this exact session and not go learn about Agile, for example? Because it powers all the things in .NET. Every single application we build, usually, let's say about 98%, is using network calls, is using API calls, is using REST calls. So that's why you should care, because you build these things every single day. You create HTTP calls every single day in all the applications that you're building. And we rely so heavily on the data that we send back and forth between our front end and multiple backends that even the smallest bottleneck can have such a big impact. Because even if we create a delay of a second, which may not sound like much, if that second adds up and stacks up for hundreds of times, that's a lot of time that you lose. Right? So that's why this is important. And there are a lot of common pitfalls because HTTP client is implemented to be very easy to use, but it can also do some very advanced stuff. And we get into those very advanced pieces quite fast because you follow guidance online. You come watch some guy on stage at some conference talk about something and you go like, that's a good idea, I need to do that as well. And that way you start using features maybe without fully understanding them. And that's where you make the mistakes. So that's why I'm here, to try and improve your life, code-wise. So what is HTTP client, really? It's a class in .NET. It lives in the base class library, and it lives in the system.net.http namespace. Well, since .NET is open source, this is the URL where you can find it. You can just read the code. I've done this for this talk, so you don't have to. It's actually quite a boring class, to be honest. It doesn't do very advanced things. Or, well, code-wise, it's not that complex. It sends and receives HTTP requests and responses. And at its core, HTTP client is just a collection of settings, right? You configure the way that your front end contacts a backend. Your own backend, a different backend, it doesn't matter. And the way that you configure your HTTP client, that's a collection of settings that you use for the communication between those two. An HTTP client instance has a connection pool. a fixed set of connections that it can create to a server. Once that connection pool runs out of connections, you're done. Your application is no longer connecting. Sounds obvious, right? Now, HTTP client in its base class is an HTTP message invoker. And HTTP message invoker is an implementation of the iDisposable class. And because we're all very good .NET students, we know that iDisposable means using statements. We can put it in a using block. Don't do that, not with HTTP client. And this is one of the first pitfalls. Now, the more experienced developers already know this. This is one of the first things that they teach you. Don't put an HTTP client in a using block. Why not? Because that means you will dispose it immediately when your call is done. And I have a demo to show the effect of that in just a second. But first, let's take a look at what actually happens if you make a call. This is the line of code that makes a call to a URI. We've written this line of code millions of times. But do you know what actually happens in the background when you call this one line of very simple code? Well, first of all, DNS resolves the IP address of the server. Oh, this is a talk about networking. Interesting. So we resolve DNS. And that's where we start the TCP dance, the whole TCP handshake, because we're using TCP connections. First of all, your client will send an SYN, synchronized sequence number, which is basically the number that the segment of incoming data should start with. Sends that to the server. Server responds with an acknowledgement of that number. The client sends the acknowledgement that it received the acknowledgement. That's just a TCP handshake. That happens every time you make a connection. Anywhere, not just from HTTP client. This is the TCP handshake. But since we're using HTTPS, we also use TLS because our connection needs to be secure. I forgot to click my button, so you didn't see the arrows. There you go, TCP handshake. Once that is done, we start a TLS handshake. The client sends hello. In that hello message, client also specifies the version of TLS that it supports and a cipher suite. Server replies with server hello. This is the highest TLS version that I can support. This is my cipher suite. Directly following that, your server also sends a digital certificate to the client. The client validates the certificate, sends an encrypted pre-master secret back to the server. The server decrypts that pre-master secret, sends the session key back to the client, and from that moment on, all the data that goes back and forth gets encrypted and decrypted. All of these things happen every time you say get async on a new instance of HTTP client. All of those steps. Just to kind of give you an idea of everything that happens in that couple of milliseconds before you get your response. Coming back to the iDisposable, before we move on, if you put your HTTP client instance in a using block and you dispose it at the end, next time you do that same call again, you go through that same loop. You do the two handshakes again. However, if you reuse your instance of HTTP client, then you won't have to because your connection is still alive. It's still there. Your TCP is connected, your TLS handshake is done, you just send a request with encrypted data. Now, after a while, that connection times out and you have to do it again anyway. But if you're doing rapid connections or you're doing a lot of calls, then this will help you save time, right? So what's in an HTTP request? An HTTP request is basically an envelope with a bunch of stuff in there. First of all, you got your request method and protocol version. Example of that is get is your method, API products, whatever is your address, your endpoint. HTTP 1.1 is the protocol. You have a bunch of headers there as well. The host that sent the message or the request. You have your user agent, which is basically what kind of browser or machine you're sending this from. The encoding, it's accepted, and then you can send user-defined headers as well. Think about bearer tokens that you send in an authorization header. That's a user-defined header, for example. And then you have your actual content, which is a serialized payload. This is maybe not the best example because a GET request doesn't often have payloads. But just to let you know. Then you have the encoding, different encodings possible, and then there's the fact that you transmit this over TCP channel. That's your request. All of this gets constructed by HttpClient out of the box. Unless you want to do custom headers and custom things in there, this all happens automatically with the default settings and so on. All right, let's have a look. Okay. I have a couple of demos with me for today. There is an API running on my machine in the backend. It's a .NET Web API. There is literally nothing in there. But this endpoint that gets the weather, there are two endpoints. Well, there are more, but these two are more important. There's the weather forecast that has a delay of 2 seconds to kind of mimic an API that takes a bit longer to do its thing and to send a result back. And then there's the weather forecasts, plural, which gives me 5 weather forecasts. I was planning on letting them return rain always since we're in London, but I forgot. All right, with that. The API is running, not in debug mode, but somewhere in the console window, that's fine. This is what I'm going to do. I have an HTTP client. I'm going to call the weather forecast endpoint, the one with the 2-second delay in the beginning. And I'm just going to let it write the response status code. And I'm going to do that 20,000 times. So for the next 40,000 seconds, we're just going to be sitting here. All right, let's go. So this is a bad example, by the way, because if I go back to the code for just a sec, switch this on. I'm creating a new instance of my HTTP client every single time. So this is everything I just told you not to do. You see the responses coming in. Oh, there we go. And after a while, this will crash because you exhausted the connection pool. It doesn't take that long. There we go. How do I zoom in here? Okay, it says only one usage of each socket's address is normally permitted. Thing crashes. Because we are creating new HTTP clients every single time. Now, I'm calling this 20,000 times, so let's say if I take the task delay out of it, the 2 seconds, then it actually succeeds because it returns fast enough that enough connections can recycle in time. But to fix this issue, I can just take this line of code out and put it outside of the loop so that I'm reusing my HTTP client. I'm not going to let it run until the end. Oh, crashes again. Whatever, I'm not going to let it run, but it succeeds now, as you just saw. All right, let's forget about this. Now, in here, I'm still just creating my own HTTP client, just creating a new instance, which is fine and all, but in general, you want to use your dependency injection for something like that. I'm having duplicate names. There we go. So, simplified version of that demo, no longer the loop, but I'm still instantiating my own version of HTTP client, and I want to make this the responsibility of my dependency container, inversion of control. This is a console application, so we often think that service collection, like the dependency injection container of .NET, only exists in ASP.NET, but it doesn't. It's a NuGet package. You can add it here in a console application as well and use it there. So if I go to Manage NuGet Packages, and I install Microsoft.extensions.dependency-injection. Let's add that. And then extensions.http. Add that. There we go. Then I can go here and create my service collection. And now I'm doing dependency injection in a console application, or I'm ready to do it anyway. Now, extensions.http has an extension method that's called @HttpClient. And just like that, I have an HTTP client instance registered in my dependency injection container. It's that simple. But this is now instead or registered not as an HTTP client, but as the HttpClientFactory, which is a factory class that can generate you HTTP clients, which is a better way of using it than creating and organizing your own instances. So let's say that we have our provider, which is services-built service provider. Then we can take out our factory, which is provider.get required service. We can get this through its interface, HttpClientFactory. We have a factory now. And with the factory, you can do client equals factory dot create client. Let's put this in comment. And if I run that, that should just work. There we go, that worked. Here's the results. So this is already a better way of using HTTP client, using the HttpClientFactory. That you get, well, this came into existence from ASP.NET, but because this is just .NET, it found its way into other platforms as well. And you can use this anywhere. Now, HttpClientFactory has a lot more options than just this. But before we go into those options, I'm going to switch back to the slides for a second. I just told you that HTTP client, you should not create multiple instances of that, right? If you use HttpClientFactory, that's exactly what you're doing. You're creating multiple instances of HTTP client. That was pretty fast of changing my mind, right? And you want them as short-lived as possible. Meaning, you create a client from your factory, you do your call, you dispose of the client. That's it. Now, why can we do this? Because all the clients that are created from an HttpClientFactory, they share the same HTTP message handler pool. That pool gets reused. So all the components from HTTP client that we want to reuse are there because of the factory. And that's what makes factory important. So you can use your short-lived objects in memory, that's okay, but you're not rebuilding your connections every single time. It's just there. You can also configure your HTTP clients with specific settings per endpoint. You can do that in a typed and a named way, and I'm going to show you both options in the next demo. Now, if you are doing cookies for your authentication, for example, be very careful with the HttpClientFactory because of the pooling system. Because of the HTTP message handler instances, you have a shared cookie container object, which means that your cookies could also be shared across your instances of HTTP clients. Be careful with that. The message handler that's in there has a default timeout of 2 minutes, and you can change that. But that's the default. That's something that's important to know. This is how you can set the connection lifetime. Why would you need to set the connection lifetime? Because if you don't do this and your DNS gets updated, meaning that your endpoint gets a new IP address, that update won't make it into your client factory. So if you don't set the connection timeout for the pulled connection, that means that those updates won't make it in. But if you set a timeout, then those connections will be reset, they will be rebuilt, and your new DNS entries will come in. Also something to keep in mind. Might not happen that often, but if you run into it, it's one of those things that you can spend a long time searching for. So in general, if you're doing HTTP clients, use either the HttpClientFactory or long-lived HTTP client instances with a pooled connection lifetime. But don't use your typed services as singletons. All right, let's dive back into the demo, which is more fun anyway. I'm switching to a different project. Set a startup. There we go. Let's run this for a sec. This is an ASP.NET project with Blazor server and just a basic Blazor template, right? If I click the weather page, this calls the API. Every time I refresh it, we get some other temperatures, weather forecasts in the application. Now, looking at the code of that page, pages, weather. There we go. We're doing the right thing. We have a reusable HTTP client. Okay, cool. We are getting a JSON string back from the API using the plural endpoints. So we're getting more than one. And we deserialize that into a weather forecast array. Weather forecast is just a very simple object. We don't really care about that one. It's just this. Okay. There's a couple of things wrong with this code. It works, yes, definitely. Is it best practices? Not at all. There's a lot of stuff missing here. First of all, we are getting a string async here. We are not checking if the call that we are making, if that's returning a correct status code. What if the API is down? Then the thing just crashes. Well, that is something we need to handle. We need to capture the fact that the API is down. We need to provide the correct error message to our user. This cannot just crash, right? So instead of using the getStringAsync, we could, for example, say, I want my HTTP response message. And I don't want to use getStringAsync, but I want to use getAsync. Copy that endpoint. There we go. Take this out for a sec. Okay. With getAsync, we don't get a deserialized response back or a string response. We get a response object. And in that object, there is the content. There is the status code as well. And that's what we need. We need to be able to check if our API responded successfully. So we have response message.statuscode, which is an HTTP status code object that we can definitely check, but there's also a helper method in here that says ensure success status code. And that method will check that status code property, and it will throw an exception if it's not in the 200 range. And from that moment on, we are inside our own code. Remember when we're calling APIs, you have to think that oftentimes these APIs are not in our control. We don't own those. We own the front end that's calling them, or the application that's calling them, but oftentimes we don't own those APIs themselves. Meaning if they give a 500 or whatever, we need to provide that to our end user in a nice way. So by calling the ensure success status code message, we are using our own .NET code to generate an exception when something went wrong. And with that exception, we're back in .NET land, and we can do try catch and the whole thing. And then we're back in our own exception management system. Okay? But since we're calling ensure success status code, which possibly throws an exception, we also need to catch that exception. So we'll surround this with a try catch. Like that. And then we have a catch. And that would be an HTTP requests exception. And then we can, for example, say exhaust status codes, whatever. You do your thing in that catch block. That's what it will do. Okay, another one that we might be willing to catch is the task cancelled exception. The task cancelled exception does not, if you look at the documentation of get async, the list of exceptions that it can possibly throw, the task cancelled exception is not there. But it can get thrown because task cancelled exception is a subclass of operation cancelled exception, and that one is there. But it's a more specific one, we need that one. Okay. That's already starting to look a bit better. But we are not using HttpClientFactory here. This is just your normal HTTP client. If you want to use HTTP clients, this might be a good way to do it. You have your instance that's there that you can reuse. You are checking the status code. You are catching the right things in the try-catch system. This is already way better than it just was. Okay. Oh, by the way, we're not done yet. What if things go right? Then we need our JSON. So then we take our response message, dot content, dot read a string async. This will take my content, which is an HTTP content object, and read that as a string. So I have my JSON. And then from there on, I can go forecast equals system.text .json.this. Oh, I forgot what it was. Which is okay, I have it right here. There we go. Just to show you that it still works. It doesn't. All right. Just to show you that it still works. There we go. It still works. Right. Okay. HttpClientFactory. Next thing we are going to do. So in order to do that, we go to the program CS, the place where in an ASP.NET application you register everything in your dependency injection container. Now, this is exactly like what we just did in the console application. I add my HTTP client. With this, I can just inject HTTP client instances in whatever class I need. It will be right there. But that's kind of the same thing as we already have. So we could, for example, name this HTTP client. We're naming it Weather API. And then we can start to configure it. For example, we can set a base address. And I forgot what the port was. 7060. Oh. Like that. Of course, this is a URI, not a string. Like this. And in this, base address is just the most simple example, right? Because you have a base address for all your APIs. And with that, I have configured a specific HTTP client. I've given it a name, a weather API, which is a key to this specific instance. And I've given it a configuration. Now, if I jump back into my weather page, then I can say, give me my AI HTTP client factory. Let's call it factory. Make it a property because I'm going to inject this like that. Let's get rid of the client. And now I can use my factory to create a client, and I want a client with this name. And then in the getAsync call, I can just throw this out. I just want that. If I put a breakpoint right here, and I run this thing, and I can't figure out how to zoom in here. Oh, there we go. It's a new laptop. I still have to figure out the keyboard. I hate how laptops all have different keyboard layouts. Come on. Okay, so the base address is filled in because I'm reusing that configured instance that I registered, using the name that I've given it. Let's see if I can zoom out again. There we go. Great, awesome. Let's continue, and it works. Yeah. The biggest thing here is I don't have to remember my base address in every single call that I make, but also those base addresses usually come from your app settings, and they are different for every environment that you deploy to. And now there's only one place where you have to keep that in mind and get that from the correct app settings, register the correct base address in your HTTP client configuration, and you're good to go, no matter what environment you deploy on. Now, that is very fun, but what I prefer over named clients, and that's just personal preference, is a typed client. So I have a class here that's called Weather Client. Weather Client takes in HTTP client using the new primary constructor feature of a couple of C# versions ago. It has a getWeatherAsync call, and it calls the API in the really bad way that we fixed previously, but it's just to keep the demo a bit concise. So don't look at these two lines of code, they don't matter. It's all about the fact that we have a client that has an HTTP client as a constructor parameter. That's where we start. Going back to program.cs, something else we can do, I'll give myself some space here. Builder.services.add HTTP client. HTTP client has a generic overload. And I can put my weather client in there. The only thing that's needed for a class to be of that type is an HTTP client parameter in the constructor. That is something it needs because it injects that client in there. We can copy this and put that in there. Obviously, we don't need the name because we are using a typed configuration now. So I'll take this away. And then go back to my weather page, where I now need my weather client. I'm going to comment all this. Forecast equals await client.getWeatherAsync. And that's what I like about it. It keeps your your view models, your controls, your whatever that's not directly calling the API, it keeps it very clean. I'm just doing a method call here, a one-line method call, instead of injecting all kinds of HTTP client instances. Let's put a breakpoint here, see what happens. All right. We are in the weather client. The client itself gets injected. The base address is there. Continue the code. That works. This is my preferred way of doing these things, using the typed clients. All right. So far, so good. Next part I want to talk about is delegating handlers. And this is where the fun stuff begins. The client factory and stuff, that's all pretty basic. I'm pretty sure that a bunch of you already knew that existed and saw nothing new. Next part is delegating handlers. Delegating handlers is a way to add extra functionality, not necessarily on HTTP clients, but on the calls that you make. It intercepts both your requests that you make and the response that you get back. And you can do stuff with that. Those handlers can also be changed. You can have, I think, as many as you can. I didn't go look for the maximum, but you can chain them. And the HTTP client handler is a part of the HTTP client. That's kind of built in. Now, if you look at the schematics here, your request comes in, goes through message handler 1, through message handler 2, through whatever HTTP client handler, which is the default one that just handles the actual thing. Go over the network, do your thing, it comes back in the opposite direction. First through the HTTP client handler, then message handler 2, message handler 1, then onto the caller. If you want to learn more about that, there's a link here. I summed up all the links at the end as well. And that will give you all the details about those handlers. Now, there are a couple of limits. You cannot change the settings in those handlers. You can change the response, you can change the request, but you cannot change the settings for your HTTP client instance because the call is already happening. So you can do that. You also can change your socket HTTP handler configuration because of the same reason. And you have to keep in mind that handlers are synchronous. Because the order in which you do them could be important. Okay, so no asynchronous handling of those handlers. A great example of one, if you're looking for a public example of a delegating handler, is in the just eat code. Just eat or takeaway or whatever it's called here. I know in most of the world it's just eat, in Belgium it's called takeaway. They have a lot of open source stuff, which is really interesting to go watch. They have an HTTP client interceptor that if they are running their system in test mode, they are not making the actual calls. They have a delegating handler that intercepts the request and just returns JSON, like a dummy data set of JSON, based on the type of request that comes in. That way, they can mock their data without actually having to build stubs or use a mocking library or whatever. They just do it using a delegating handler. That's the link towards that one. That's an interesting read. Oh, that was too fast. Let's have a look at handlers. Close our tabs. We will reuse this one. I have prepared some handlers. We'll start with the first one. So a handler is a class that inherits a delegating handler. From delegating handler, it overrides a method called sendAsync. In sendAsync, you get your request message, cancellation token, and you can do whatever in there. Well, except for the limits that we just described. For example, in here, I'm just logging that a request was made. And then I continue the request onwards to the next handlers all the way down the system. To use that, there is the add HttpClient call that we do here. And then we can add a add handler, HTTP message handler. That was a thing. And we take the logging handler. There we go. Just like that. This will crash. And this is the first time that I remembered that it will crash. Because if you add the HTTP message handler to an HTTP client, it uses your dependency injection to get the instance from it. So you have to register it first. Let's say a transient logging handler. There you go. Now, if I run this, and let's put this to the side and take this one. So this is my console output for the running application. If I now make my call, then it hits the breakpoint that's still there. Zoom in a bit. You see here the logging messages that I made in the handler. So the request passed through the handler first, then got handled, and then came back. Because if you go back to the code, you'll notice that this happens first, then we pass on the request further down the line, and then it comes back and logs this. Okay, so let's go back for just a sec. See, we log handler, logging request 2. We send the request along the line, and it will wait here until my request has passed all handlers, went to the API, and then came back. And then eventually, we'll reach this line. Okay. Let's create a second one. And this is kind of an example where handlers are really good at. You can use them for injecting your bearer tokens in your authorization header, for example, which is what we're kind of mimicking here. Just injecting the authentication header value. We do the same thing, register it as, register it in dependency injection container. Add the message handler here, auth handler. There we go. Looking back, also there, 2 console write lines. So the first messages is always handler in full caps, and then received once everything comes back. The order in which they are added is auth handler first, then logging handler second. Let's see what happens. You see, we first pass the authorization handler, then the logging handler, then the actual message goes through, the response comes back, first through the logging handler, then the authentication handler. So it passes handler 1, handler 2, comes back, handler 2, handler 1, according to the diagram that we've seen in the slide. All right. Another system that uses handlers that you might not know about, well, you might not know about the fact that it uses handlers, is OpenTelemetry. OpenTelemetry has a package called instrumentation.http, for example. And let's add an exporter as well. Very fast for those who don't know OpenTelemetry. OpenTelemetry is kind of an agreed upon standard of doing metrics, instrumentation, logging, all those things. It's not .NET specific. It's an agreed upon formats across technology. Most modern technology stacks have an implementation of OpenTelemetry. ASP.NET relies on it heavily. If you've ever seen the Aspire dashboard, that just collects OpenTelemetry. In this case, I have a console exporter, meaning that all the OpenTelemetry data that I'll be showing will be output in the console, just like we've seen now with the logging statements. Now, I've added those NuGet packages. I'm going to create a meter provider from the SDK. Create meter provider builder. And that contains an extension method that says add HTTP client instrumentation. Then we add the console exporter. So we see our output, and then we build the thing. That's all there's to it. What this does is, what the HTTP client instrumentation does, is it registers message handlers or delegating handlers into your system. And it relies on those handlers to do its thing, to create all the logging data. So I'm just making some calls here. Let's go see what happens.
Maybe a quick question.
Yes?
What is the order? If you first do a registration of OpenTelemetry or after you do your own client?
That is an excellent question. So the question was, if you add those OpenTelemetry delegating handlers, are they added first or after your own or somewhere there? I'm not sure. I should look that up actually. I would say. Sorry?
Should we see it in your logs?
Yeah, that's fair. Well, it's not logging my calls exactly. It's now more logging the. It's mostly logging the connection between Visual Studio and Blazor now. That's all the output that you see here. It could be that they use it as a primary handler, which always comes first. And there's a specific way of creating a primary handler, which makes sure that you're always first in the chain. But it's open source. We could look that up if you want to. Good question. I'll write it down for next time I do this talk. Okay. Coming back to the slides. How are we on time? 12 minutes left. All right. Another very important part of doing network calls is your resiliency, because calls fail. Sooner or later, they will fail. Network is down, internet is down, server is down, someone is down. And those failures are normal. You just need to make sure that you handle them. And there are several ways of doing that depending on the severity of what's happening. It might be that the server was just too busy to respond to your request that time. And if you try it again, it might just answer and nothing happens. Might also be that the backend is being updated and the next 5 to 10 minutes, it won't be able to answer. All those things might happen. You don't know. You have control over the system that you're building, which is the application that makes the calls. You don't have control over the receiving party. So we need some patterns to do that. And we can't be too naive about this. Because let's say we are contacting Google Maps. We are using the Google Maps API. You make calls to it. Millions of people make calls to it every single day. Me just walking around London makes constant calls so I can track myself in 20 years where have I been in London. All of that works. Let's say that goes down. Millions of people are trying to connect to Google Maps, but it doesn't work anymore. It comes back online. Can you see what happens? Those millions of people start requesting their data to the API that just came back online. That's called the thundering herd. That server, well, in case of Google, I hope it scales, but that server might go down again because it's just too many requests at the same time. And you want to prevent that. And there are techniques for that. Mostly, you don't keep retrying. You increase the timeout between your retries. But also, libraries like Poly can add a jitter to it, which means that you say to your resiliency library, I want to retry every 3 seconds. But if everyone does that, you have the same issue. So what they do is they create a jitter. And what I mean with that is those 3 seconds, this one time it might be 3 seconds, but then it might be 3.2, 3.1, 3.15. It kind of creates an offset. And it's as random as they can get it. So if all the libraries or all the applications that use this library use that jitter thing, then the thundering herd will get spread out. And your server has time to breathe, which is important for servers. Now, Poly, as I've mentioned the name before, I don't know if you've heard of Poly, but it's a very popular open source library that does resiliency. It does retry patterns. It does circuit breaker patterns. It can do the timeout, rate limiting, fallback to other endpoints. It can do stuff like that as well. Poly has become so much the default in .NET that it's included in ASP.NET. The default ASP.NET templates use Poly. Microsoft has an extension library that adds extra extension methods on top of Poly, on top of ASP.NET that configure your Poly settings. Now, a circuit breaker pattern that I mentioned is, well, exactly that. It flips a circuit when your server goes down. So what happens is, as long as your request succeeds, your circuit stays closed and connections go through. But if, depending on your settings, the server doesn't respond for X amount of times, the circuit opens. And this is something that you can check. That's, again, an exception that gets thrown. And you're basically leaving the server alone because it didn't respond. For X amount of time, time-based, the circuit stays open, and calls don't go through. Like, Poly will actually stop the call from happening. It doesn't leave your system. Then the circuit can go half open, which means it will try to reach the server to see if it's back online. If it's back online, then the circuit will be fully closed again, and calls will start to go through again. This is basically stopping you from making too many unnecessary calls to a server that's down, allowing the server to come back up, also allowing your application to provide decent messages to your end user. Let's have a look at that. Set a startup project. This is once again a Blazor project. It calls 3 different endpoints on that same API with some successes or failures. There's the, I don't know if that's big enough. Do it like this. There's the eventual success that sometimes fails. If you retry it a bit, then it will succeed. There's a complete failure that will always fail. And then there's the hit or miss that will sometimes fail, sometimes succeed. Those are the 3 different endpoints I have in there. If it fails, it returns a 503. That's a failure it does. Okay, let's make this a bit more resilient. Let's see what we have here. We have an HTTP client. We have a logging handler in there to do some logging. And then the base address with a timeout of 30 seconds. I'm going to add Poly to this. And as I've mentioned, there's an extension library. Microsoft.extensions.poly. Install that, apply, accept. And then to make sure I have the correct program CS, let's do some housekeeping. There we go. Okay, I'm going to create a retry policy. I have my HTTP policy extensions. I'm going to handle HTTP errors. And let's say I want to retry async 3 times. Now, on my HTTP client registration, I can now also add a policy handler and give it that retry policy. And that's a nice thing that I find about these extension libraries. The way that you are now extending your HTTP client feels very much like it belongs in that way of working. It's the exact same way of working, even though we're now using an external library. So it feels very natural. Let's see what happens. I'm going to do it like this again. Let's do the eventual success. What's going on? Of course, that succeeded. This is this one. Yeah, you see 503 is coming in. You see it retry a bit. Well, it retries 3 times, and if it doesn't succeed, it still fails. Stop trying to sign me in. All right. So that's just a simple retry policy. But this is what creates the thundering herd. It just keeps going. A better option is the wait and retry async, in which you can say, I still want to retry 3 times, but I also want to increase the time in between. So you can give it a time span in seconds, of seconds that it needs to wait between options. If you then use the math library, and you say, for example, I want 2 to the power of the attempt that I'm in, like that. So attempt is an integer, and it is the number of attempts that I have done. And every time I'm going to take 2, which is just an arbitrary number, you can do whatever, 2 to the power of 1, 2, 3, whatever attempt I'm in, which increases the timeout between each attempt, right? Meaning the server has more time to recover. And for the sake of our time, I won't be showing the actual thing again, but this just waits a bit longer every time. Now, the final thing I want to show you is the circuit breaker. And for that, I have a policy right here. That is the circuit breaker policy. It's also from the HTTP policy extensions. I create a circuit breaker. After 3 failed attempts, the circuit opens for 5 seconds, and then you have the different events that fire. If it breaks, then you can do things like logging, showing a message. If it resets, meaning the circuit is closed again, calls can again go through, you can do stuff. And if it's half open, if it closes halfway, if it goes to check if the server is online again, you can do stuff as well. And then I can do get circuit breaker policy. Oh, it's in the policy builder. Oh, it's here. Get circuit breaker policy. I put it in the wrong place. That's okay. There we go. And with that, I've configured poly using the same way of working as HttpClient. All of these demos are on my GitHub because I don't have enough time to run them now. If you want to try them out, there is a link right here. The slides are on there, the demos are on there, everything is on there. If you look at the slide deck, the previous slide of this one that I just skipped over real fast are all the links that I've used to build this presentation. So there's a lot of extra information on there. Both on HttpClient specifically, but also on TCP, TLS, and all those things. With that, we are out of time. I thank you all for being here. If you have any questions, feel free to come up to me or find me in the hallway. Thank you very much.